Professor Lee Smolin, welcome to
Yes.
Hard Talk.
Thank you. It's a pleasure to be here.
You seem to believe that theoretical physics has lost its way. Why do you believe that?
The fundamental search for new laws of nature, and especially to complete the revolution that Einstein started early in the 20th century, seems to have run into problems. Principally because physics over the long term has been marked by great advances in thought, audacious ideas working out, but great advances in experiment that paralleled that, so that theory and experiment walked hand in hand to deeper and deeper understanding. And for the last more than 20 years, we have not had the parallel tracks of theory and experiment. Theory has gone ahead in string theory and quantum gravity and other beautiful, audacious developments, but they have not had the support so far of experiment.
Before we get into the detail of string theory and why you believe it can be so damaging to physics, you say there's been no groundbreaking discoveries in 25 years, but surely that simply reflects that we human beings have pushed the boundaries of what we know very far already. So inevitably, it is now going to be tougher to discover new things.
I don't think so. To me, that comes across as an excuse, as the same kind of excuse if you have a company that was very successful in software and some high-tech business, and you haven't really had a success in 2 decades. You couldn't say to your directors, well, we've reached some boundary and it's getting tougher. Your directors would say, well, find a new business or hire some new young people and find a different direction.
So are you saying that physicists are suffering a sort of fundamental failure of the imagination?
The problems are challenging and are tough, no doubt. But my sense is that what we failed to do is, in a sense, we've been too successful, we've been too used to success, and we've forgotten how audacious science is. And we've forgotten how outrageous sometimes the ideas that turn out to be true are and seem to the experts and the authorities at the time. We've forgotten the lesson of Einstein and people like him, who come from the outside but have exactly the right insight and the right idea. In a sense, as science has become successful, it's become more businesslike, more quality-controlled, more assured, and the kind of controversy and audaciousness and disagreement that, if you look at the history of science, marks the key developments. Because when we don't know the answer, different people, different experts have radically different responses, and that openness, the inclusion of the different points of view, like in anything else, like in politics, like in business, is essential for progress.
You make it sound like within, and we're talking about some of the smartest, brightest people in the world,
Sure.
within that community of super intelligent people, there's almost a sort of fear of going against current orthodoxies.
Well, I don't want to generalize completely like that. There are...
But tell it like it is. Is that the way it is in some quarters, in some of the top universities?
There is what I would call a premature consensus around certain ideas. The way that I see the development of science, disagreement is central to science, controversy, conflict, because we don't know what the right way forward is, because different people will emphasize different questions, different viewpoints, different ideas. And in my understanding, in my reading of the history of science, science does something wonderful, which is it has a process which converts disagreement and controversy to consensus. But that requires that experts be brought kicking and screaming by the weight of evidence to agree. And how does that happen? How do we... First, we have to be open. We have to understand that we could be wrong, but second, we need the weight of evidence from experiment to convince skeptics that an idea they thought was ridiculous is the right way.
Now, if there is a convention amongst theoretical physicists right now, the conventional thinking is based around string theory. And I know that you have devoted an awful lot of time to saying to your peers, your fellow scientists, you've got this wrong. String theory isn't going to provide the answers. So if you can, as simply as possible, explain to me what string theory is and why you believe it's so flawed.
String theory is one of a number of different attempts to unify the different forces and the different particles in physics. Fundamental physics in the 1970s got to a view that there were 4 fundamental forces and roughly a dozen different kinds of fundamental particles, and we're more ambitious than that. We would like to understand the different forces as all aspects of one force, because that's happened before, this kind of unification. And we dream that maybe the different kinds of particles are just different states or different manifestations of one fundamental state, one fundamental...
I mean, in essence, this is... String theory would be a theory of everything that
Yes.
would explain all phenomenon, from the phenomenon inside particles, the very smallest objects, to what happens in the universe with black holes and everything that we see in cosmology. It would link the lot in one theory.
Absolutely.
And isn't that something that we should be looking for?
Of course, we are looking for it. And an important thing to say, the most important thing to say, is that string theory is a good idea, but it's one of half a dozen different ideas presently on the table about how to make this unification. And to be convincing, it lacks two things. One of them is a theory to be convincing must make predictions, which are precise enough and clear enough that an experiment that we could do would prove them wrong. Otherwise, it's not testifiable. It's not testable. And string theory, for a very interesting reason I can tell you about, doesn't do that. The other thing is it should come in a coherent whole. It should start with a beautiful principle, like the principle of indeterminacy of quantum mechanics or the principle of relativity. And there should then be a beautiful equation that flows out from that principle to a myriad of consequences. In string theory, we don't know if there is such a principle. We have pieces of something. It's like having different glimpses of some beautiful structure, some beautiful idea. But more than 30 years of investigation by many of the smartest people, the most gifted mathematicians and physicists, have failed to lead to an insight into what that key principle is, if there is one. So I'm not saying anything very complicated. I'm saying, given that this one attempt, which is beautiful, which is well motivated, is not the only attempt, and given that it succeeded on these two fronts, let's leave it there, let's continue to study, but let's open the door to other ideas, to other approaches, and especially to the kind of audacity that some young person like Einstein could come in and show us the way.
But to be clear, you are not ruling out the possibility that elementary particles arise, as string theory has it, from the vibrations of these sort of notional strings inside particles, and that if you get down deep enough, if you take away all the wrappings around particles, you will find this string. You don't rule that out.
I don't rule that out, but then the next question is, so what is this string? So what is it? I mean, the cartoon is, there's a little one-dimensional thing flying through space, and that's the root of a key issue. Einstein taught us that space is not a background that things move in. Space is a network of relationships that are ever evolving, ever dynamical, part of the world. The geometry of space evolves and changes, wiggles, just like anything else, just like electromagnetism, just like particles and so forth. And string theory has not so far taken on board that crucial insight of Einstein's theory of general
relativity. But maybe
relativity.
Einstein was wrong, because in the end, didn't Einstein posit essentially four dimensions, you know, the three spatial dimensions plus time? Well, string theory is very exciting because, as I, again, understand it, it posits the notion there could be 10 dimensions. Dimensions that we don't yet understand, but are out there somewhere.
You know, this idea about extra hidden dimensions is not a new idea. It arose, in fact, first in 1915 as a competitor to Einstein's thinking about general relativity. And general relativity turned out to be right experimentally. By 1919, that was clear. And notice very quickly, and the theory, the speculation about extra dimensions turned out to be wrong. Again in 1919, there arose again the speculation of unification through extra dimensions. Einstein first embraced it. He thought it was the most beautiful thing he'd ever seen. And then he understood that it was a bad idea, the wrong turn in the road. And the idea failed. Now, and if you like, I can tell you why it was the bad idea, why it was the wrong turn in the road. But to see this idea rise and fall and rise and fall, it's a very attractive, very seductive idea. But it's fundamentally flawed, this idea of extra dimensions, for reasons that Einstein understood already back in the 1920s.
You have generated a lot of anger with your insistence that string theory is a dead end, that physicists should in many ways simply abandon. I mean, I spoke actually to Professor Mike Duff, who's a theoretical physicist at Imperial College London, and he says to suggest that string theory has achieved nothing of note in the past 25 years, which you have suggested, is, in his words, simply silly.
Well, I have not, in fact, said that string theory has achieved nothing of note. And many of the people who have expressed anger, of my friends and colleagues who have expressed anger, have not actually read the book. Now, what I have said is that string theory has not succeeded as a theory of fundamental physics. It has not proven itself, and it has not, so far, we have not found a way to formulate it as a coherent theory. And it's very important to separate that. I have nothing against the activity of studying string theory. I've spent years at it myself. Many of the people who do it are friends.
You were an advocate of it at one point
my
in
second
your career.
book, for example,
so
strongly
you're sort of a
advocates
heretic
it.
in a way. You sort of had
No,
the belief
I
and then
think,
you abandoned it.
I think, you see, the point is this is not about belief, but the stakes are very high, and therefore the standards should be very high. The stakes are how we see the universe, what the universe is, what space is, what time is, and ultimately what we are as living creatures inside this universe that evolves in space through time.
Well, why is it going to change any of those fundamental things to our perception of ourselves and our place in the universe, if we can or cannot ultimately falsify, prove string theory?
So I'll give you an example.
Go on.
Okay, I was telling you about this divergence of views about space, whether you see space as something that exists prior and then things that move in it. We call this the absolute view of space, versus space as a network of ever-evolving dynamical relationships. Okay. Well, there's a completely parallel issue in political theory and in theory of the law. Is society something which exists with a prior, absolute, God-given structure that we have to fit ourselves into, or is a society an ever-evolving dynamical network of relationships that we evolve as we will it and as we struggle with each other and argue with each other over the best form of it? It's profoundly different ways to conceive of ourselves and our existence in society, and the same parallel issue is how we see ourselves as living creatures in a universe of space and time. It's the same discussion and the same issue. And to me, it's fascinating. I didn't know this originally. It's fascinating to see our colleagues who worry about what society is and what law is arguing over the same issue that we're arguing about in physics. So that's one reason it matters.
I want to pick up on that deeply sort of philosophical point later, but before we get to more philosophy, let's get to a few practicalities. Because another point you make is that essentially 25 years has been lost because of the prevailing dogma of string theory. But again, many of your peers, scientists I imagine you respect, say 25 years is the blink of an eye. It's absurd and indeed deeply impatient of you to say after 25 years, where there hasn't been a groundbreaking breakthrough, oh, well, the entire theory is a waste of time. Give it more time.
If string theory were the only thing on the table, what else could we do? Okay. The fact is that string theory is not the only thing on the table, and some of what's at stake here is that the other approaches, which are ideas of other people who are also experts, who are also brilliant, have for peculiar...
You're talking about yourself? I mean, because you have other theories.
Well,
Are you suggesting that there hasn't been enough oxygen sort of in the scientific atmosphere to allow your particular view of...
I'm not talking so much about myself because I'm a peculiar person. I've worked on all these different ideas. And the ideas that I work on are not mostly mine. I'm very good at seeing a good idea and then taking it somewhere. And I'm very flexible. So I've worked on string theory, on loop quantum gravity, on many of the different approaches. So I think I can sit in a position and judge fairly and say, I think we could use more oxygen over here in this side of the room.
Right.
Okay. The other thing is that in my reading of history, in my study of history, of science, which I have done to try to figure out why we're in this situation, what impressed me is that when the right idea was put on the table, the experimental test came fast, and the passing the experimental test came fast. General relativity, 1916, the eclipse that proved that light bends, 1919. Quantum theory, 1905, the notion of a photon. Experiments start to come in 1907, 1908, 1911, and so forth.
Well, let me stop you there, then, because that's a very interesting point, and you have said several times in this interview the problem with string theory is that there are not experiments that are being done that will...
There are not even predictions for experiments.
Right. Well, let me put this to you. We in Geneva see the construction of this massive underground tunnel where very soon they're going to start running protons around at almost the speed of light. Protons going this way and this way. They're going to smash into each other. And there, some scientists believe, you are going to see things which will actually back up string theory. And then you'll have some hard evidence to go with the theory. Do you buy that?
One won't be testing any prediction of string theory there. The Large Hadron Collider is very important. Experiment is always
Some scientists believe you might even, in this massive collision, you might even see signs of the string.
You might, and that's if certain parameters, which are variable in the theory, are adjusted to a certain extreme value so that the strings can be very large. But the crucial thing is that supposing it's not seen, that doesn't disprove string theory because that parameter could just have been dialed smaller. So in every case where there's something compatible with string theory that might be seen at the LHC, if it's not seen, that just rules out one way that the dials might be set.
The LHC being this collider.
Yes, yes. So what I mean when a theory makes a test, when a theory makes predictions, in the history of science, it does much more than that. It puts something on the table and says, if this is not seen, my theory is wrong.
Well, all right, leave aside string theory for a moment then, but stick with the collider under Geneva.
Sure.
Do you believe, as some do, that whatever we find from it will, in a sense, recreate the moments, the split seconds after the Big Bang, and because it will recreate that, will tell us an extraordinary amount about the way the universe was created and how it works?
Well, the way that you put it is sort of rhetoric and publicity.
Well, forgive me for that.
No, but every time we build a new accelerator, we probe nature at higher energies and shorter distance scales. And in a certain sense, we get closer to, quote, the Big Bang or the beginning of the universe. And with the Large Hadron Collider, we get about a factor of 10 closer.
You excited about that?
I'm very excited about it. Experiment is the most important thing. And a remarkable thing is that we've been waiting for this experiment for 30 years. And this experiment goes a factor of 10 in scale. Okay?
But factors of 10, you know, if we are a long, long way from understanding the origins of the universe and how it works, then a factor of 10 may not help us very much.
A factor of 10 goes from a foot to an inch. And we theorists have been unable to come to consensus about unambiguous predictions for what we should see going from a foot to an inch. Okay. String theory and its alternatives and rivals, okay, are about what nature is like 20 factors of 10 smaller. Okay? And all that we're arguing about when Mike Duff and I, have an argument is how much weight we should put on one of a dozen different ideas about what nature is like 20 factors of 10 out of the range of experiments. Some people are so confident of their theorizing that in the absence of experiment, they have a kind of what I think is a premature confidence, a premature consensus that we must be right. And I think that that's bad for science.
What if there actually isn't a unified theory of everything? What if there are no rules that govern everything, i.e. quantum physics and the theory of relativity don't have any connection? Have you thought about that?
Of course I have. I think that they must, because nature is a unity. There's one world, things fall.
Well, as far as you know.
Good point, but nonetheless there's at least one world, and in that one world where we live, things fall and they're made of atoms. And I would like a view of nature that allows me to understand both in the same conceptual picture. And we don't have that.
Well, you would like it. That's the point, isn't it?
Of
you
course,
want neatness.
of course.
You want a sense of design. You want to believe that all of this hangs together.
Yes.
But what if it doesn't?
Let's leave that for people in future generations to sort out. See, I don't think that science goes after ultimate questions. If you ask, is there ultimately an ultimate law of nature? I mean, as you started the program asking, Maybe, maybe not. There are very interesting provocative philosophers on both sides of such ultimate questions. My job as a physicist is to take it to the next step. Einstein left an unfinished task. Einstein invented relativity, taught us to understand space and time as a dynamical entity of relationships, and Einstein started the road to quantum physics, the decisive break with Newtonian physics. Okay. He left the revolution unfinished, and the job of my generation and the generations older and younger, hopefully not too many more generations to come, is to finish the revolution that Einstein started.
Does it matter, though, if you don't? I mean, you know, again, to put it crudely, there'll be a lot of people watching this show who will think that perhaps it's better to spend the billions, for example, that the CERN project has cost, spend the billions on seriously combating global warming, seriously trying to find a cure for cancer, to conquer global poverty. These are things that would make a difference to human beings living on planet Earth today. Is what you are talking about and finishing Einstein's revolution going to make a difference to most human beings on this planet?
I think it will, in the same sense that the change from before Newton to Newton made a difference that people talked about, shopkeepers talked about, business people talked about, diplomats talked about. If you go back to the 17th and 18th century, there was a profound effect of the revolution that Newton made. Because before that, people saw society as hierarchical and those hierarchies as built in from God, and nature also as hierarchical. And Newton did away with that hierarchy and gave us a world of atoms all the same. And John Locke, a friend of Newton's, fashioned a political philosophy, right here in London where we are, okay, as a copy of Newton's natural philosophy that became the blueprint for democracy as it then developed in Europe and then spread around the world. So these changes are profoundly important.
What you see of the state of the revolution, do you believe it will be completed in your lifetime?
Of course, yes.
You sound very sure about that.
I'm an optimist, and my view in my book is not pessimistic, it's optimistic.
I'm just about to say we're out of time, but I want to end on optimism, so let's leave it right there. Professor Smolin.
And for the last more than 20 years, we have not had the parallel tracks of theory and experiment. Theory has gone ahead in string theory and quantum gravity and other beautiful, audacious developments, but they have not had the support so far of experiment.
Before we get into the detail of string theory and why you believe it can be so damaging to physics, you say there's been no groundbreaking discoveries in 25 years, but surely that simply reflects that we human beings have pushed the boundaries of what we know very far already. So inevitably, it is now going to be tougher to discover new things.
I don't think so. To me, that comes across as an excuse, as the same kind of excuse if you have a company that was very successful in software and some high-tech business, and you haven't really had a success in 2 decades. You couldn't say to your directors, well, we've reached some boundary and it's getting tougher. Your directors would say, well, find a new business or hire some new young people and find a different direction.
So are you saying that physicists are suffering a sort of fundamental failure of the imagination?
The problems are challenging and are tough, no doubt, but controversy and audaciousness and disagreement that, if you look at the history of science, marks the key developments. Because when we don't know the answer, different people, different experts have radically different responses, and that openness, the inclusion of the different points of view, like in anything else, like in politics, like in business, is essential for progress.
You make it sound like within, and we're talking about some of the smartest, brightest people in the world,
Sure.
within that community of super intelligent people, there's almost a sort of fear of going against current orthodoxies.
Well, I don't want to generalize completely like that. My sense is that what we fail to do is, in a sense, we've been too successful, we've been too used to success, and we've forgotten how audacious science is. And we've forgotten how outrageous sometimes the ideas that turn out to be true are and seem to the experts and the authorities at the time. We've forgotten the lesson of Einstein and people like him who come from the outside but have exactly the right insight and the right idea. in a sense, as science has become successful, it's become more businesslike, more quality controlled, more assured, and the kind of...
Professor Lee Smolin, welcome
Yes.
to Hard Talk.
Thank you. It's a pleasure to be here.
You seem to believe that theoretical physics has lost its way. Why do you believe that?
The fundamental search for new laws of nature, and especially to complete the revolution that Einstein started early in the 20th century, seems to have run into problems. Principally because physics over the long term has been marked by great advances in thought, audacious ideas working out, but great advances in experiment that paralleled that, so that theory and experiment walked hand in hand to deeper and deeper understanding.